Before we start with our geological experts, we also have a short introduction by our colleague Dori Egre. She works for Energy Club and will give us an overview of the situation with paks. So coming to the authors of this very, let's say controversial study, is Kurt Becker. He is a well-known researcher in earthquake geology, active tectonics and seismic hazards at the University of Vienna. He is also very often a member of teams with IEA missions, NSWAC, which became well known for the stress tests, NAGWA, but also the Austrian Ministry of the Environment, with a focus, of course, on nuclear safety and natural hazards. We have also Tamás Bodoki. He's a Hungarian geophysicist and expert in applied geophysics, seismic explorations. And he was the director of the Lorenz Geophysical Institute of Hungary. And so he's also very experienced in this issue. We will have presentations after Doris' introduction. After that, I'm happy to announce we will have a discussion among us, but we have, I see already 2 or 3 experts from the field, one in the legal questions, because of course the part that we have to inquire about is what do these facts mean, of course, for the licensing, environmental impact assessments, ESPO convention, are there any implications? So I would ask you now, Dori, to start with the introduction. Thank you.
Thank you, Patricia, and I would like to welcome everyone as well. Before continuing with what is happening in Hungary concerning the nuclear expansion, I would like to shortly introduce the joint project and Energia Club as well. So in the joint project, European NGOs, research institutions, they have been cooperating for almost 20 years on safe and sustainable energy issues, with a focus on anti-nuclear activities in Central and Eastern Europe. I see now that multiple people from the joint project have joined us today as well, so welcome to them as well. Energia Club is an organization having spent close to 30 years in creating new awareness in Hungary concerning energy issues. With our research, training courses, wide-reaching communication, we aim to make energy producers, users, and perhaps even political decision makers to act with regards to energy usage. We are working with joint project on the nuclear expansion in Hungary, which is the concern of today's meeting. As you all probably know, we only have 1 nuclear power plant currently functioning in Hungary with 4 nuclear reactors, but the PAKS-2 project is undergoing, and we will have 2 new reactors to ensure the continued use of nuclear energy. But this has been a hotly debated topic for more than 10 years. In 2009, the Hungarian parliament gave its provisional acceptance for the possible expansion of the existing nuclear capacities. And in the following years, preparatory inquiries were taking place for the establishment of the new reactors. However, the documentation of these inquiries were not made public, which resulted in multiple years of litigation. In 2011, the parliament accepted the so-called National Energy Strategy, according to which Hungary will keep using nuclear energy. But the turning point came in 2014, which I think was one of the most shocking decisions in political history in the last 10 years, because without a tendering procedure, agreements were signed with Russian state-owned company Rosatom to supply 2 new reactors, and Russian Federation financing 80% of the investment costs, which amounted 10 billion euros. In 2016, the paks 2 project company submitted its site license application to the competent authority, which is the Hungarian Atomic Energy Authority. According to the project company's website, acquiring the site license was a two-step process. The first step was when the project company compiled the program of the site investigation and evaluation, which was approved by the Hungarian Atomic Energy Authority in 2014. They state that the program was made with broad and detailed knowledge on the site, which we will cover today. During the second step, the site investigation and evaluation program was implemented. The goal of the site investigation and evaluation was to identify every natural and human circumstance, characterize their effects on the design of the nuclear power plant, and verify its safety. The site license application had to prove that the site was fit for establishing a nuclear power plant. The key statement of the site investigation and evaluation was, according to them, that the site was suitable for accommodating new nuclear power plant units. The site features were defined by technical and scientific standards, and as these were taken into account, they say, the safety regulations, new units could be designed and established. And finally, in 2017, the Hungarian Atomic Energy Authority authorized the site license application. And it was Átlátszó that reported first in 2017 that the site of the NPP and the planned expansion does not comply with the International Atomic Energy Agency's earthquake safety recommendations because there is an active tectonic fault line that passes under nuclear facility. Less than 10,000 years old traces of earthquakes were found on the surface in the immediate vicinity of the site. But despite the report and the extensive investigative work done by Átlátszó, the state carried on with the project. Since then, the implementation and the construction licenses have been submitted. And obviously, it's quite concerning that new scientific results come to light, and the Hungarian Atomic Energy Authority says that they are aware of the results, but they are still saying that everything is okay, there is not a danger to the plant site, and this is what we are about to discuss today. Thank you.
Yeah, thank you very much. So I think we continue with the geological presentations. If it's okay, Kurt, would you start? We introduced you, I think, before you were here. So
no problem with this. Thank you. I'm
were later
ready
than I
to start.
Please.
Okay, I don't have the screen under control. Thank you all who participate for spending this one of the first hot summer days with a hot topic in front of the computer. Now, my purpose here is to give you some insight into the results of a recently published document that was myself and Esther Hintersberger, who was at that time working at the University of Vienna with me on active tectonics, active faults, paleoseismology, and such topics. So we did this project for the Austrian Ministry of the Environment, which changed its names from time to time, but this doesn't care us here. With the background to evaluate from a geological point of view the site documents that are available for paks 2. If we can move on. So we did not make a full scope assessment of these documents. We focused on a very narrow focus. And this is highlighted in the uppermost lines. The paleoseismological assessment of the siting documents focused on the potential of surface displacement by an active geological fault. This would be called, in the terms of IAEA and the international regulations pertinent to nuclear safety, capable faulting. Why did we do this? Now, we read the Hungarian governmental decrees on nuclear safety requirements, and there are two of them. They are listed here, 7310800. Sorry for these complex names. The first one here claims or requires that potential occurrences of permanent surface displacement on the site shall be analyzed. And I know that nobody of you is now really aware of what is a permanent surface displacement. I will show this in the next slide. Much more important, the next decree, 7311100, says if the potential of occurrence of a permanent surface displacement on the site cannot be reliably excluded, the site shall be qualified as unsuitable. So please note, it's not necessary to prove permanent surface displacement. It's necessary to reliably exclude the possibility of surface displacement. And this was our task in this report, to evaluate, are the Hungarian geological documents reliably excluding this permanent surface faulting as a hazard for the site of paks 2. Now, what is permanent surface displacement? No, sorry, next slide, please, Gabi. These are the documents that we evaluated. We did not do any own research. We just looked into 3 types of documents. The first on the left-hand side is the geological site report. Extremely valuable literature, thousands, maybe thousands of pages of renowned Hungarian geologists and geophysicists examining the site and producing a report which is really comprehensive and containing all, or hopefully all, relevant data from the site. This is one branch of the basis. The second one is the site safety report. The site safety report has been done by the company MVM paks 2. And they distilled their site safety report from the geological site report. And we also looked on the distillation process. Is everything which is necessary or which is important and described in the geological site report also found its way into the distilled product? I can take this in advance. Not everything that the geological community found out is in the site safety report. And second, and the third thing is that we checked the site permit, which was then issued later on by the Hungarian Atomic Energy Authority. So this is the basis of our work. And now let me solve this with the next slide, the secret of what is permanent surface displacement. We are somehow talking about earthquakes, but not the shaking through an earthquake, but the fault that fractures the Earth's crust, and some of the faults by producing strong earthquakes also fracture the Earth's surface. This is shown here in a recent example from New Zealand, 2010, the Darfield earthquake. And you see that the blocks in the meadow, the Earth's crust blocks, moved as the arrows show, one to the left, the other one to the right. And they displaced this water channel for something like 2 meters. This water channel survives. He has no problem. But guess there is a critical infrastructure, a water dam, he would not survive. A chemical plant would have its problem. A nuclear power plant would have severe problems to survive such a displacement should it disrupt significant parts of the equipment of any of such facilities. The next slide shows other effects of the same earthquake. And you can see the road on the left-hand side could not sustain the forces of the Earth. No way to do so. You see all the cracks, and you see all the fun that this little, I hope, future geologist, I'm sure that he studies geology meanwhile, and specialized on paleoseismology, standing in one of these gaps that were produced in the earthquake. Remember this little guy? We will see him again during the presentation. So this is the effect that we are searching for, or that we are evaluating. The next slide, please, shows that this is not an academic discussion. This type of hazard, fault capability, affects nuclear plants. And the most recent one was the Niigata earthquake in Japan, who affected the Kashiwazaki Kariwa nuclear power plant. You can see that the earthquake, the fault, destroyed the access roads, but it left aside the reactor. So they had a whole bunch of luck with this earthquake and the fault, which was capable at this time and ruptured the Earth's surface. So this is the hazard that we are looking at. Now, the next slide brings me to paks. We were near Japan and we were in New Zealand. Let's come back to Central Europe. The map on your screen is a tectonic map. In the middle of the map is the site with a yellow polygon marking the site of paks. And from the top to the bottom, more or less in north-south direction, you can see blue lines denoting the Danube that passes the paks 2 site. The gray polygons are faults, geological faults, active faults that move the Earth crust in this area of the Pannonian Basin. The most important one is the DHFZ, which is the, and now I have to look this up, the Dunaszent-Görgi-Harta fault zone. Sorry for my bad Hungarian spelling, which, as you can see in this map, is located right below the site. Now, all the triangles and the blue waves that are, and the red stars and the other stars denote evidence for large earthquakes and displacement of very young sediments that were collected in the geological site report. Very unfortunately, the corresponding figure, which looks very much like this in the site safety reports, excludes all these evidences. There is no evidence marked in the site safety report, no red star, no seismite, no green triangle. Next evidence that is collected for, next slide please, in the geological site report. This is another style of showing the Dunaszent-Görgi-Harta fault zone. I don't want to explain the details in too many words. Here in this circle, the site is right in the center. This is because the geologists had to analyze a circle with 50 kilometers diameter radius around the site. And you see the black line that comes from the lower left to the upper right. This is the fault zone that we have just seen in the first slide. And in Hungarian language, you can see all these bubbles that point to some places, denoting some earthquakes, denoting some geomorphological evidence for the activity of the fault. This is on the left-hand side. This is the geological site report. On the right-hand side, and there is a spelling error, this is the site safety report. This has been produced by MVM paks. And you see all the information on the nice neo-tectonic, on the quaternary active tectonics is missing, and the figure on the right-hand side. Now, let's continue to the next figure, please. Oha, can you put once more? No, then I don't know what's the case here. It should show another type of figure, but we can continue 2 slides more. The next, please. Now, no, just the one before. Looking at the site now, not in the region around the site, this is the map from the geological site report that denotes the extent of the Dunaszent-Görgi-Harta fault zone, which is delimited by the bold red lines here. So you can see that these bold red lines cover the southern part of the site. The site is here showing the existing reactors, and with the yellow polygon, the site where the future reactors should be placed. And you can see that the fault zone extends quite far into the area where the future reactors should be, and it even extends into the area where the reactor blocks should be. This is denoted by the yellow broken line here. Now, how do the geophysicists come to this? Yes, thank you, Gabi. If you move south, you can also show the existing power plant with the mouse, maybe. Yes, this is here. So these are the existing reactors. moving to the next slide, shows you a profile. This is hard to digest for non-geologists and non-geophysicists. This is a cross-section through the Earth's crust. It is crossing the fault zone that we have now seen looking down to the surface in a cross-section. What you see is the uppermost few kilometers of the Earth's crust. So it's really going deep down because earthquakes happen deep down in the crust, but the faults come up to a shallow surface, as you can see indicated by all the red lines here. And you can see that the faults down, further down in the section are very narrow and they get much wider going upwards. And this is a situation where geologists get lyrical and they call it a flower structure because the green faults in the depth, this is the trunk of the flower and the leaves of the flower, the blossom, are the red lines closer to the surface. So you see that this type of fault widens to the surface. It branches from one main fault deep, deep down that produces eventually an earthquake up to dozens of faults which arrive eventually at the surface. So this is the architecture of this type of fault that is underlying the nuclear power plants in paks. The next slide, please. So here we are back to the map that we have shown just before. The section that you have seen is just opposite side on the Danube, opposite to the power plant site itself. The line PA22S approximately locates the section that I have just shown in the last slide. Now, this is the figure which is shown in the geological site report. Let's continue to the next slide and look at a similar figure, but only similar figure, which is in the site safety report. To the left, the geological report, and to the right, again, I'm sorry, with a spelling error, the site safety report provided by paks, MVM paks. Compare the width and the location of the faults. On the left side, the geologists claim that the fault extends into the area where the reactor blocks should be. On the right side, MVM paks claims that this fault does not touch the reactor blocks. This is one of the points that we want to clarify with our Hungarian colleagues in the future. Is this just by chance or is this on purpose, or what happened between these two maps? This is one of the things that need urgent clarification, in my opinion. The next slide, please, Gabi. Now, you have seen this map already. Just the new thing is now a white arrow in the lower left that points to what is written in blue. There is PA21-2 Arok. And this is a trench that was excavated for paleoseismological purposes, and which I will show in the next slides. Before I show the trench, the next slide shows again a cross-section, a seismic section, depicting the layering of the sediments in the subcrust, in the Earth's crust. But this time we are not looking down kilometers deep into the crust, but this time we are looking only few tens of meters down. So what we see are the youngest most, the uppermost sediments. And in the lower panel, you see colors like yellow below. These are old, relatively old sediments. And what is above, the pink and the green, these are extremely young sediments, sediments of the Danube that were deposited in the last couple of 100,000 years, with the youngest, very youngest sediments on top being few tens of thousand years old. And what the Hungarian geologists and geophysicists have been drawing here, they have been drawing 10 individual faults that come up almost or really to the surface, cutting the youngest sediments. This is shown in the lower panel, the red lines that really come up to the surface. Now, based on this, the paleoseismologists in Hungary got some appetite to excavate a trench. And you see on top, there is a red bar, which is marked with next slide. So this is the location of the trench. So they excavated only 2 of these faults that are shown by the geophysicists. They had a close look on 2 out of 10 faults. This I would like you to keep in mind. Now the next slide is very easy. Geologists having fun, creating a trench and hoping to get a good exposure that shows a lot of funny and interesting geological structure. So this is the working method. You look for a caterpillar. This excavates a profile of the soil. And by looking on the profile of the soil, you do your the conclusions and interpretations. This is done. The result is shown on the next slide. This has been produced by Halas and his co-workers, the Hungarian colleagues who did the paleoseismology. And it is showing a profile that corresponds to one of the walls of this trench. What we see the horizontal stratification of the sediments of the Danube. So all of these are Danube flood sediments. You know, when you live near to the Danube, a Danube flood leaves some sand on the riverbank or some silt or some mud, and one flood after the other builds up this sediment pile. What you also see are the red and orange lines. These are the faults that cut these sediments. And you see in the horizon a sediment layer that is leveled with E1, event 1. Many of the faults, mostly the red ones, terminate at E1. Why do they do so? Now, at the time when sediment E1 was deposited, the fault ruptured, broke the surface, and the faults were at the surface. This happened something like 20,000 years ago. It could not fracture the upper sediments, the fault could not fracture the younger sediments because they were not yet deposited. They are not yet here. After the earthquake, younger sediments were deposited up to the level of E2, nothing happened. And then again, an earthquake happened with faulting at the surface, creating the faults that come up to the level E2. This was something like 19,000 years before present. And since then, new sediments have been accumulated, and fortunately enough, not a younger event of surface breaking faulting occurred because the younger sediments here seem to be intact. So we learn from this, there are 2 events, 19,000 years and approximately 20,000 years ago, of faulting, which fractured at the Earth's surface at this time, not the present Earth's surface, because the present Earth's surface has not been yet deposited 20,000 years ago. How do the structures look like? The next slide will show you this. This is the soil profile in person. You see the stratified, horizontally stratified sediments. All sediments are from the Danube, flood sediments. And in the left picture, in the middle, they are disrupted by a funnel-like structure. This is the surface breaking fault. And if you closely look at the bands of these sediments, you see that they are offset. They are fallen down into this funnel, and you see that the funnel is filled with something very different from what is to the left and to the right of this funnel. On the right picture, a similar structure is seen just a little bit left of this colorful plate in the middle. The next slide gives you an impression how this can be interpreted. Here is our little boy, the nowadays paleoseismologist. Now, this was a structure similar to what we have seen or learned in New Zealand. This was a structure that pertained to the Earth's surface, created this funnel-like crack, which then later on, of course, was filled with something else, as well as the crack where our little boyfriend is standing will be filled up in the future again. So this is the paleoseismological interpretation of the situation excavated in this trench. The next slide. Very unfortunately, this is the only trench that has been excavated. So the only strong evidence for, or also maybe against, surface breaking faulting that is available in the whole bunch of documents which cover a few thousand of pages. Another promising location would be PA22S. This is where the white arrow now points, on the other side of the Danube. And here the seismologists have acquired another very promising seismic section, which is shown in the next slide. Again, showing the uppermost meters of the sediments that are underlying the meadows and the forests along the Danube. And here you can see 16 individual faults counted by the seismologists and geologists doing the interpretation here. Very unfortunately, we have no further evidence whether these faults came up further, closer to the surface. We don't have evidence of their age. We don't have evidence how much offset they have, etc., because no data, no paleoseismological data have been acquired there. So the next slide, now you can relax. We leave the field of geology, we come to some conclusions. And the first conclusion is not very scientific, but rather popular, I think. We have tried to draw the extent of the Duna-Szentgörgyi-Harta fault zone on this mock-up of the future and existing nuclear power plant. This is a picture that you can download from the paks 2 homepage. And by locating the buildings and the shoreline of the Danube, it's fairly easy to figure out where the fault runs in this picture. But the fault is here denoted by the reddish polygon. And you see that it's all below the existing power plant and it extends into the future power plant, based on the data that are available from the geological site report. So this is the first conclusion. Yes, there is a fault. This is active fault. It underlies large parts of the paks 2 site. The next slide. Here, the first conclusion is paleoseismological data from the trench next to the site confirm the existence of faults that led to permanent ground displacement in the past. They did so 20,000 years ago, they did so 19,000 years ago, and they will do so in the future. Because geological tectonical faults are not switched off because somebody builds a construction on top of it. What did MVM paks make as a conclusion? In the site safety report, you can read seismic events occurring in the research area are not able to significantly displace the surface. It is the fault planes cannot be considered capable. We wonder, and we really would like to know how MVM paks came to this conclusion, looking at the pictures that you have seen already from the trench. We concluded in our report that this is not in line with the geological evidence described in the geological site report. And we make here a rather strong statement for scientists, but I think it is supported by what we did as a comparison between the reports is that this is contrary to the principles of good scientific practice. The site safety report downplays certain data and does not account fully for the contents of the geological site report. This is one of our conclusions. The next slide, please, Gavin. Second, again, paleoseismological data confirm the existence of faults that lead to permanent ground displacement. What is the conclusion with respect to the Hungarian governmental decree? I read again the decree. If the potential of occurrence of a permanent surface displacement on the site cannot be reliably excluded, the site shall be qualified as unsuitable. Cannot be reliably excluded. So if we don't care about what we have seen in the trench and just focus on cannot be reliably excluded, I would say that one trench, 85 meters long, on a fault zone which is 1 kilometer wide and consists of dozens of faults that come up to the surface is not sufficient to exclude the possibility of permanent surface displacement. Not to talk about the proof that we have seen from the trench, which is 85 meters long. And you remember the crack that would have looked similar 20,000 years ago to what the little boy here is standing in. The last slide, I think. We conclude from the geological site report, mainly from the geological site report, but this is also stated, I have to say, in the site safety report, that a wealth of geological and geophysical data proves that the Dunajec-Görgi-Harta fault zone is an active fault. This is an interesting statement, not so much with respect to Hungarian regulations and IAA regulations, because yeah, this is not a good site, but it's not the site exclusion criterion. But if you look into Russian codes, the NP 03201, which is a code dealing with the siting of nuclear facilities in Russia, it clearly states it is not allowed to locate nuclear power plants on the sites directly situated on active faults. Full stop. No comment else made in this regulation. Why is this interesting? Now, the background is that the Russian provider should provide the nuclear island and the whole nuclear power plant. Having in mind that the site in Russia would maybe not be found suitable as a nuclear power plant site. This is the end of my presentation. The last slide is just again the mock-up showing the extent of the fault zone below the nuclear power plants. Thank you for your attention and sorry for doing so much geology.